Okay, we should be good. Yep, we're good. Okay, so in this video, we're gonna sort of branch off of autonomous for a second. We'll come back to it in another video, actually, the next video. But for today, what I wanted to introduce you all to was the idea of sensors, getting information from our robot to begin with. Because right now, what we've been doing is sort of just telling our robot to do things, like telling a motor to move, telling a controller, hey, if I press this button, do this. So, what we want to do today is really use the sensors on our robot and see if we can do some, pretty interesting things with them. So, there are going to be two main sensors I want to talk about, but before I even do that, I just want to talk about the idea of how a sensor works in general. So, let's open Paint here, familiar Microsoft Paint. Let's say we've got a robot here. I'll just give it a title, robot. Cool. Actually, let's say this is the robot's RoboRio, right? Now let's say we have a sensor here, right? Let's just call this sensor S. It can be anything generic. I'll go into more specifics later, but I want to get a basic idea across first. So previously what we have, let's say we had a motor here, right? What we do is basically the gist of it is this RoboRio here is sending a direct command to the motor, right? And that's all it's doing, right? It's not doing anything else, just saying, hey, motor spin. What we want to do is somehow take information from the sensor, send it to the RoboRio, and then use this information. So do something with this information and actuate our motors. So that's the general idea of what we're going to be doing in today's video. So there are a few different types of sensors I want to talk about today. So let's start off with one that's going to be pretty useful in the context of autonomous, since that's what we're fresh off of. So there's something the main sensor that we use within autonomous. So when you've previously worked with autonomous, right, everything was time controlled. So we did this, like if we wanted to code a 90-degree turn, we have to figure out how long we wanted the motors to spin for in order to actually get the 90-degree turn to work, right? Now, rather than doing it off time base, because if you think about it, right, when your surface changes, let's say you had a surface with more friction or a surface with less friction, that time, that constant is going to change, right? So rather than deal with that sort of variability, what we can do is use something called a pigeon IMU, or I'm just going to call it a gyro sensor for now. So effectively, what it is it's just a small sensor that goes on your robot. Hold on, let's see if I can get a. Never mind. So all it is a small little rectangle, and you'll see it on the robot once you start experimenting with it. But it's just a small rectangle that's connected to our robot. And all it does is it returns our heading, or otherwise, the angle of orientation that our robot is facing. So let's say I'm going to open a new window. Paint. So let's say, for example, we've got a robot here. And let's say right now, moving forward, our robot's currently at 0 degrees, right? So if you want, try imagining something like a protractor in your head, right? So if you have something like this, what the pigeon sensor, the gyro sensor, tells us effectively is how much is what our heading is. So what angle our robot is facing at. So if I'm moving straight right now, my robot's facing 0 degrees. But if I were to rotate the robot, and I don't know, maybe somehow it ends up like this, facing this orientation. Let's say the heading is no longer 0 degrees, but something like 45 degrees, right? That is what our gyro sensor tells us. You can imagine this being pretty useful, right? If we can get the angle that our robot is moving at, then all the code that we've written for 90-degree turns, or for coding at an arc, or for ending our robot at a specific angle, all of it can easily be alleviated just by using this one sensor. So we're going to talk about integrating that code in a second, but let's talk about some other sensors. So on our current swerve robot, actually, we're using a sensor called a beam brake. So let me get something. Let me get a diagram running here. So I want you to imagine your garage door, for example. So let me draw a picture of it real quick. So let's say that's your garage door right there. And if you notice on the side of your garage door, if you've ever taken a look, there are these two little sensors here. And these sensors have these like little laser-like things on them. And effectively they go across like that. And so what this tells us is, so when this beam is complete, so when it's completely extended across both ends of the garage door, that means that we effectively aren't intercepting it, right? So there's no interference with the beam. And so, the garage door knows that, okay, there's no one there, so no one's crossing it. That means I can safely close my door and we're good to go. Now, let's say this is you, right? And you want to go outside, but you accidentally go outside while the garage door is closing. So you're going to intercept and cross that beam. And what happens is this beam gets interrupted. So, oops, let me get my eraser. This beam's interrupted. So now part of it is gone, right? And so what a beam break can tell us is, like on a binary basis, whether or not the sensor's been interrupted. So if it is, okay, cool. That means we know someone's there. The garage door needs to stop. When it's not being intercepted, that means, all right, there's no one there. We can continue closing our garage door. Now the same principle applies for a beam break. It's a beam break sensor. It's actually the same thing. So you can imagine on a robot, right? Let's say this is the conveyor for our shooter, right? So let's say the shooter's up here, right? You've got your flywheel, your other wheel, and let's say that's a ball. What beam breaks allow us to do is actually keep track of how many balls are within our robot at once, right? Because if you think about it, if you have a beam break here, or rather somewhere near the shooter, like right there, what you can do is say, all right, if we cross this first beam break, that means there's a ball somewhere in here. And once we cross the second beam break, we know the ball's already been shot. So it's effectively allowing us to manage the state of our robot, to see how many balls are within the robot at once. And that's pretty useful, right? That's information that's useful that we can use within our robot to determine, hey, how many balls are we actually shooting? What are we allowed to intake a ball because we can't hold more than two balls at once? All of that. So that's useful. That's why beam breaks are useful. And the third type of sensor, and that's pretty much that's going to be the focus of our video today, is the built-in encoder on the Falcon motor. So the Falcon 500 motor is unique in comparison to other motors in that it actually has its own built-in sensor. And what that sensor allows us to do is determine, how many times the motor has spun relative to some unit of measure. So like something like meters, we can see how far the motor has spun, or in the case of Falcons, it's called ticks. We can also determine how fast it's spinning. Now, the key part is what I just said, how fast. Because right now, when we've been commanding our motors, we've been doing them for some percent output, right? For like, say, 90% of what the current is. But here's the thing. It's 90% of power, not 90% of the potential speed of a Falcon. So rather than commanding it based on some percentage of power usage, what we're going to do instead is actually command it at a specific velocity. So in this case, because a motor rotates, right, we use a unit called RPM, so it's revolutions per minute. And let's say I wanted to command a motor at 4,000 RPM, right? We can use a sensor. We can get the sensor on the Falcon, or we call it an encoder. We can get the encoder data and effectively command our motor to move at this exact velocity. Now, the tricky part with this is determining, well, how exactly are we going to get to that velocity in the first place? So how fast are we going to get it? Because you can't directly actuate a Falcon motor at a specific velocity. Like there's no method that says, hey, spin at 4,000 RPM. Rather, we have to do some math ourselves and figure out, all right, are we getting at that RPM? And what can we do with this RPM? So that's pretty much what we're going to be doing today. So figuring out what's the best way to get to get to an RPM, maintain an RPM, and see, in general, how we can command our shooter to work off of this RPM. So before we do that, I want to introduce you to some new methods for your drivetrain so that when we start working with the Pigeon more in the future, you'll be set. So all I want to do is I'm going to head back to code, my lovely VS Code theme, and we're going to go into our subsystem, so our drive subsystem right here. And we're just going to add a few methods. So just want to iterate something. So you guys actually already have worked with the with some of the sensors. So like something like get selected sensor position. that tells you, all right, this is how much my motor has moved. So that's something we're going to be basing things off of once we work with RPM. But for now, let's just work with our pigeon here. So, but before we even do that, what we need to do is create our pigeon. So I'm going to go up here, and we'll just do it up here. Private pigeon IMU, and we'll just call it gyro equals new pigeon IMU. And we're just going to pass in, just like we did with our motor. You see how we pass in a CAN ID or an ID for the motor? We're going to do the same thing. Now, you'll have to check with the robot to see which ID it is, but for now, I'm just going to put in 11 just as a temporary number. Okay, so what exactly do we do with this gyro, and in which methods do we actually use it? So let's head down to our code. And what I'm going to do is I'm going to make a method called get fused heading, or we can call it get heading. So we're going to write public double get heading. All we're going to do is return gyro.get fused heading. So that's a method that's built in with the Pigeon IMU class, something we can use. We just get our heading. Now, we get our fused heading. I'll talk about the difference in a second. Now what we're going to do is actually create our method called get heading. Sorry for the confusion there. I'll explain in a second. And what we're going to do is return math.remainder, and we're going to get fused heading and enter in 360. So effectively, what we're trying to do, so because of the way the pigeon works, right? Get fused heading is just a method that's built into the pigeon class that just gives us a raw heading. So it's not actually limited to something like 360 degrees. So it's not going to automatically limit itself after you complete a full revolution. It's going to go over. So we use this function here, get heading, to just say, hey, if we end up spinning more than 360 degrees, or if we need to spin a significant amount, we have the ability to, circumvent that and just say, hey, get my heading and then give me the right number that I need to get the angle that I need. So that's the most basic way of understanding that. And then one thing I want to do is just have the ability to zero our heading. I'll talk about why that's important in a second. So public void zero heading. Zero heading. And we're just going to say gyro.set fuse heading. Let's put in 0. Now the reason why that's useful is because let's consider the following scenario, right? We have a robot moves forward and it makes a 90-degree turn. Currently, the robot thinks we're at 90 degrees, but let's say we want to move the robot more. Technically speaking, if we wanted to make sure we were on axis, we'd have to make sure that our current position was still 0 degrees, right? Because if you think about it, if the robot's facing this way, we want 0 degrees to always be at the front of the robot, right? But right now, the front of the robot's facing to the right. So we have to manually reset the position of our robot and say that, hey, we need to actually move at 0 degrees. All right, so that's all I want to say for right now in terms of pigeon, because what I want to talk about is something called trajectory planning, and that uses the pigeon a lot. So we're going to talk more about it, don't worry. But for now, this is, sort of the basics of our pigeon, just getting our angle in the first place. And if you want to give it a try and put a smart dashboard output number to get your position, go ahead. Or sorry, get your heading. Go right ahead and see what values you get. Give that a try for me. All right. So what we're going to do now is move on to talking about actually using the sensor on our Falcon motors. And what we're going to do is something called closed loop control. So closed loop control is just another fancy way of saying that we're going to command our motors at a specific velocity, right? So that, just alluding to what I said earlier, I want to command my motor to move at 4,000 RPM. And to do that, we need to use something called closed loop control, which involves something called a PID loop. So, but before we even talk about all of that, we need to actually set up our motors so that we can actually use their sensors in the first place. So I know you already might have a shooter subsystem, but I'm going to go ahead and create another one actually. And we'll call it command. And we'll call it shooter subsystem closed loop. gonna start fresh just so we can work our way up. Okay, cool. So within our class, first we're gonna just declare our two motors like we've always been doing. So public, we'll make it of type WPI talent FX. We'll call it shooter motor 1. Those need to thanks. And again, just put in your constants. I'm going to leave it at 6 for now. I'm not entirely sure. I don't remember what it is, but just check the robot to make sure. You can transfer your constants over as needed. Shooter motor 2. Let's put 7 for that one for now. Just again, make sure you oops. I'm just gonna add a question mark here saying all right. So the main goal for our sensor or our code here is to set up our motors so that we can properly use them to actually get the to actually command it at a velocity in the first place. So in order to do that, what we're going to do is within our constructor, we're going to first configure these motors at factory default. Config factory default. And what this basically does is it basically gives us a clear ground to work with, right? So there's no predetermined, sort of software on the Falcon that could potentially interfere with the math that we're doing that commanded at an actual velocity. So we're going to do the same thing for shooter motor 2, obviously. And let's just set these motors to go on coast mode for now. Set neutral mode, and then the neutral mode.coast. And then we'll do the same thing for shooter motor 2. Okay, cool. So now what we're going to do is configure the sensor on our motors. So shooter motor 1, and the method is literally called config selected feedback sensor. So config selected feedback sensor. It's going to be of type talent FX feedback device, and so the arguments are passing in. Integrated sensor. So the integrated sensor is a reference to the sensor that's actually built in onto the Falcon. So this method allows us to configure a sensor that we want to use, whether it be some sort of external encoder. But in this case, because we're using the built-in encoder on the Falcons, we just say it's the integrated sensor. And then then we'll just type in 0 and 30, and I'll explain what those arguments are in a second. So if you look here, it takes some integer here, which we're not going to talk about now. We're going to talk about a little bit, and then just takes some timeout. And so the timeout is just a periodic check value. Don't worry so much about it. We usually just leave it at 30 milliseconds. And we're going to do the same thing for the other shooter motor. Alrighty. Looks good. Okay. Now what we're going to do is configure our outputs. So what we want to do is just give our motor some sort of restrictions within it to make sure that, hey, we're not going, too fast potentially. So this is something called config nominal output. And basically what it does is it allows us to say, all right, in a normal stage, when the motor is idling, we're not going to move, right? Because we don't want it to move. But then the maximum state is just going to be the peak power that it can get, which is in this case just 100% power, right? We don't want to go over that. So we're going to do launcher motor A. Oh, sorry, not launcher motor A, shooter motor A. Get those words confused all the time. Dot config nominal output forward. And we're going to say 0, right? Because that's all it really needs for that. And now we're going to do the same thing, but for backwards. 0. Now we're going to do the same thing for shooter motor 1, except we're going to config a peak output forward, and in this case it's just 1. And notice I was asking for a percent out. That's using 1. This represents 100%. Now we're going to do the same thing. So shooter motor 1, that config peak output reverse. I'm just going to set that to -1 because it's moving in the opposite direction. All right, now we're going to do the same thing, just, it's just for freedom under 2, so feel free to copy and paste this if you want to just change this to a 2. It's the same thing. Cool. All right, now comes the part where we talk about some of the configuration for the math that we need to do on our motor. So to actually command these motors at a velocity, we need to use something called a PID loop. And I'm just going to explain that real quickly. So PID. Now, the P stands for proportional, the I stands for integral, and the D stands for derivative. Now, you might be thinking, oh, these are calculus terms. Are we going to use calculus? Um, well, in programmatic wise, we're not going to directly use calculus, but some of the calculus concepts do relate to it. But rather than worry like, oh, I need to know calculus for this. No, you don't. You need to just know the logical idea behind this. So here's the idea behind PID. So the P stands for, actually I want to introduce another variable called F. It's called feed forward. I'll talk about that too. So the P stands for proportional, right? And what this does is it's essentially just some proportional constant that allows us to reach some RPM that's pretty close. So usually P is actually sufficient enough for us to reach that RPM, because if we have this one constant, then we can command our motor to spin relative to that constant, and that's usually enough to get our motor to work. Sometimes what happens is we might accidentally, go over, or sometimes we might lose that velocity. So imagine if you have your robot shooter, right? So you've got the flywheel here and the flywheel here, and you have a ball going through. That ball going through is going to restrict the movement. It's going to slow these two launchers down, right? So what happens then is we use this I term, and this I term tells us, okay, how fast, or at what rate essentially do we accumulate that velocity back? So how fast do we actually get that back to begin with? And this might cause some fluctuations, right? Because it might just rush up and go up to your velocity. It might come back down. Depends. Now our D term is our derivative term, or another way you can view it is a dampening term. So sometimes if your P is still too much, you might consider adding a D term or a dampening term to, reduce the effect that the P has within your loop. And then you have a feed forward. And the feed forward really, you could say, does most of the work here. And it's actually, like it implies feeding. I like to think of it as like feeding RPM into the motor. It's commanding it to move. And the more feed forward you have, the more your robot will actually overshoot. So what I want you to do is, what we're going to do actually is I will give you PIDF constants that do work for our robot. But rather than me giving them to you, I want you to figure them out for yourself. So let's first set them up, and then I'll show you how you can do that. So to set them up, what we're going to do is launcher motor A, not launcher, shooter motor A, or shooter motor 1 dot config underscore KP. And it's going to ask us for its slot ID. Don't worry about that. Just hit 0 because it's the integrated sensor. And it's going to ask, okay, what value do you want? We're going to put 0 for now. And this will not move your motor, but I'll talk about that in a second, what I want you to do. So config underscore ki, so this is our interval term. Just put 0 and 0 for now. KP. I'm just going to put 0 and 0. Sorry about that. And then shooter motor 1 dot config underscore kf 0 and 0. Now you can just copy and paste this and do the same thing for shooter motor 2. Okay. So what I want you to do is after this, after you have this program, what I want you to do is only use a P loop. So we don't need I, D, and F terms. You can leave those at 0 for now. You don't need any of these. Only using a P value. I want you to think, okay, what sort of numerical constant will give us a good proportional value for us to get up to RPM? So, and I'll give you a hint, the answer is somewhere in between 0 and 0.5. So don't think anything crazy like that. So somewhere between 0 and 0.5 will have some value. Now what I'm going to do is in comments here, I'm going to give you the actual value for our shooter, but I don't want you to use these now. I want you to experiment with yourself and see how you can actually do that. So the first thing we're going to want to do, however, is actually give us an RPM so you can actually viably test this. So you can change your P and see the actual change in RPM depending on how you're commanding it. So here's what we're going to do. We're going to make a method to actually run our motors. Actually, sorry. Before I do that, because we made a new shooter subsystem, we just need to do a few things. So shooter motor 1, just configure that so that's inverted. So set inverted and then invert type. Oh, we don't need this one to be inverted, or it depends on how you have it set up. So I'd refer to your previous subsystem to determine which one you actually had inverted. That's a capital I. And then shooter motor 2 dot set inverted invert type dot invert motor output, because this one we want inverted. Okay, cool. So just refer to your subsystem again to figure that out. Okay. Before we do that, I just want to make a quick constant. So public int target velocity. And for now, you can pick whatever velocity you want. I'd pick somewhere in the thousands. So let's start with 4,000 for now and go from there. So we have a target velocity. Okay, cool. So target velocity is saying, hey, this is the velocity I want you to move at. So let's have a method called public void set shooter speed. I'm going to pass in a speed. Now, all you're going to do is do launcher, or sorry, not launcher. I keep getting those mixed up. Shooter motor 1 dot set, and then Talon FX control. Oh, that's Talon FX control mode dot velocity. So we're going to command it at a specific velocity. We're going to do so for a speed. And shooter motor 2 dot set, and same idea again. So we've got that, and that's and then what I want to do is actually never mind. We don't need to do that right now. We're fine. So yeah, there's the value that we're passing in. Now, what I want to do is set our zeros. So just default public void set 0, or we'll call it stop launcher or stop shooter, and then shooter motor 1 set Talon FX control mode dot percent output 0. Same idea for motor 2. All right. So one thing that I actually wanted to make clear is that when we command for velocity, you can see obviously here we've got velocity closed loop, right? But another thing you also want to make sure when you're actually testing and testing for your PID in general, so because that's what I'll show you how to do next, is actually getting your printouts and all of that, just setting that up for you, is one thing that you want to be sure that you're doing is keeping track of your tests and seeing how you can improve to begin with. So let's say you started off with a p-value like 0.25. That's just a hypothetical example, right? What I want you to notice is how the robot is actually getting up to that RPM to begin with. So once you toggle your command to run, what I want you to notice is how your robot is actually getting to that RPM to begin with. And once you do that, you'll be able to see, all right, is it getting up smoothly? Are we actually achieving that RPM? Is it going over and then dipping down? What's actually happening here? So it's important to keep track of that, because, you'll eventually realize that, all right, we might actually have to command this a little bit differently. We might have to actually change our p-value. Okay. And one more thing you have to realize is that this velocity that we're passing in, right, that this velocity right here, it's actually not um, in RPM. Rather, it's in native ticks per unit per 100 milliseconds. So yeah, there's a little bit of a weird sort of conversion that we're going to have to do. And so to sort of help us with this conversion, one thing that I like that we have in our program is something called a unit conversion class. So all it is it's basically just a method that does the math for us, so that when I command an RPM, it converts the RPM into the native Talon ticks. And when we get something in ticks, we can return that as an RPM. So all we're going to do is just make that real quick. It's a quick class. So you can say in your robot, you can have a new file. It's just going to be a raw class. You can call it unit conversion Java. We're just going to make a few methods. So public static double, we'll call it native Talon units. So native units to RPM. We're going to actually need the native units in the first place. And we're going to say return, and don't worry about the math here. Just have it down just so you have it out with you. Divided by 2048.0. Make sure that's a 0.0 so you don't end up with integer division. And then public static double RPM to native units, double RPM. And this is just return RPM divided by 600 times 2048.0. All right, cool. So we just have those two quick methods that help us determine, hey, what are our actual units to begin with. So what we're going to do instead is so we pass in a speed, but the speed is going to be in RPM, right? Because obviously in our heads, we don't know what Talon effects units are. That's like not conventional to us at all. So instead, we're going to say is unit conversion dot RPM to native units, and we're just going to pass in our speed. That effectively will allow us to command this at the Talon native units for velocity. So let's just recap. Because Talon Effects doesn't actually use RPM as their native units, we need our own unit conversion class. And to do that, we have this. Yeah, we need our own unit conversion class to actually make that conversion in the first place. All right, so that's it for setting speed. And what we can do now is just configure our output. So we can say that we can do that in periodic. So in our subsystem periodic, where are we? Initialize, execute, and finish. We have to make our periodic method. To do that, you can just call this public. So a periodic method, effectively what it is it's just something that runs continuously while the subsystem's in use. So public void periodic. Oop, we have an error. We are of an override. Actually, we can just do it in execute. It'll be the same thing. Don't worry about what I just said. Okay, so within execute, all we're gonna do is do smart dashboard dot put number, and all we're going to put is just our velocity. So within smart dashboard dot put number, we'll call it current motor RPM, and then we'll say unit conversion dot native units to RPM. And then we actually need to get those native units in the first place. So we're going to make a method to do that. So public void get RPM, or sorry, not get RPM, let's say get velocity for now. And we can just return one of them since both motors are chained together. So return shooter motor 1 dot get selected sensor velocity. And we just pass in get velocity here. Not typo. Ooh, that's void. I'm going to make that double. Cool. All right. So this is going to give you your current motor RPM, and for the heck of it, we'll just print out our target RPM too. Target RPM, just so you can see how far off you are, and then I think we have a target velocity. Yeah. So again, just change this target velocity whenever you want to commit it. Make it 4,000. All right, and that should be good. That should get you set up for closed loop control. So again, experiment with these values. So go ahead and give that a try. See how far you off. Again, only use a P loop and see how close you can get. I'd say if you're off by 100 RPM, that's pretty good for your first start. And then I'll give you the exact values in a moment. Okay, hopefully you tried it. So this one here is 0.275. We do have an I term at 0.00012. Our D term 0.1, and our feed forward term is 0.03. And it's the same for these guys as well. It's all the exact same. All right, cool. So now our last thing that we need to do is actually just make our method, actually run this to begin with. So in order to do that, we're just going to make a new shooter closed loop command. So command shooter closed loop command. Cool. Okay. So first thing we got to do is make our subsystem. So public shooter close, not shooter closed loop command. Shooter subsystem closed loop. Let's call it shooter. Was new shooter subsystem closed loop. There we go. Okay. Now within our constructor, right now, if you look, because we're passing in our RPM here, we're passing in our RPM here. What we can say is that we want it to run at 4,000. So instead, rather than make this, something that you input, let's just make it something that we can actually get. So our target velocity right now is 4,000, and so rather than having to deal with multiple constants at once, let's just not input a speed for now, just make things easier, and just input target velocity in here. So you only have one number to change. So just whenever you want to change your velocity, just change this number for now, and that'll be good. Okay, so within our constructor, we need to add a requirement, and it's going to be shooter. Okie dokie. Now that's pretty much all we need, and of course we need to pass in our shooter subsystem to shooter closed subsystem closed loop. We'll call it S, and we can say shooter equals S. Alrighty. And loop. Nope. Never mind. We can ignore that for now. All right. Oh, I know what did. We accidentally declared it when we shouldn't have. Shooter. Oh, that didn't work either. Oh, I think this is because it needs to be the first line. That's why. Oh, weird. Did I miss anything here? Because we're not able to add our requirements. Interesting. Because we got everything in our constructor. Weird. Okay, it's fine. We can ignore this for now. That's totally fine. Everything will still work the same. Okay. So all we're gonna do, it's very simple. In execute, we're just gonna say, shooter dot, and then what do we call our method? Shooter dot set shooter speed. And that's it. We already have our speed inputted in our class, so we should be fine. And yeah, that's pretty much it. And because we already did all the conversions, this is all that we need to do. So um, obviously, by now you should know how to add this into your robot container so you can map it to a controller. So go ahead and do that. And then once you're done, open Smart Dashboard and go ahead and test your PID loops. And if you got any questions, feel free to let us know. So the main gist of it is today is just working with sensors, seeing how we can interact with the sensors to actually make our robots do more complicated things, like actually spinning it for RPM in the first place. If you got any questions, feel free to throw it in the programming chat. Otherwise, we are good. So, thanks for watching.